Hey everyone. So in this video we want to talk about the other main materials we can create with the RBD material fracture. We've looked at the concrete version now and we will keep working with this most of the time later on. But in this video we want to look at wood and glass. And both materials will be covered in later video in more depth. This is really just to give you an overview over the RBD material fracture. Now for the wood material we've already seen an alternative in the Voronoi fracture video. And this is actually something I personally prefer, and in the future I will use the Voronoi for wood. Although to be fair, glass is actually pretty well covered with RBD material fracture, and we will look into a couple of problems though that come with this in later videos. So quick overview what we can do with RBD material fracture. So let's start with wood. And with wood now before we look into every single element of the wood fracturing, let's quickly analyze what side effects is trying to do here. This is an already destroyed version of a log here. So if I let this fall down, you can see it looks like this. This is what you would get with a couple of adjustments that we're going to look at in a second. And the idea here is actually that side effects tries to recreate what happens in reality. So let's quickly look at a reference. What you can see here is basically two things. Wood in reality has a structure, like fiber that goes along the main length of a plank, but usually when you break it, it breaks perpendicular to that. A break that is, in a zigzag basically. And this zigzag line comes from the actual fact that we have a fiber-based material. So basically you could talk about three elements: the horizontal lines, the vertical break that we see here, and then in the vertical break again, the horizontal kind of, let's call it zigzag. In the setup we will see in a second, we call the fiber of the wood the grain. The cut is obviously, the cut where it breaks. And to make sure that the cut is not straight, it is actually creating a zigzag line, like here, by representing the splinters that are coming from the horizontal fiber structure. So grain, cut, and splinters are the three elements we will look at. Here's another example. We have the fiber of the material, and then when it breaks, this fiber is represented in form of splinters. So we have the horizontal lines, let's call it the grain. Then we have the cut, and the cut is influenced, so turns into a zigzag line through the splinters. And this is what we're going to see when we look at the RBD material fracture. And let's start with a simple tube here and turn it brown, because obviously now this is wood, obviously. And when we now drop here an RBD material fracture onto this, then first we have to wait for the concrete calculation to happen, which is not what we want. So we switch it to wood, and now we get a different set of tools. And in the beginning, we see what we just talked about, the grain, which is the vertical lines that you can see here. Let's actually visualize that by visualizing the name attribute. There you go. And then we get the pieces. And you can see there is, well, it's not super easy to see, but there are vertical lines that we will see more clearly in a second. Then we have the cut. So the breaks along the length, which is here, and then down here, the splinters, they are responsible for those zigzag lines. But on top of all this, and this is why we can't see the grain very well, so the fibers, is that there is a cluster activated by default. And that's the first thing I would recommend turning this off, because it, changes a lot the overall result. So here you can see, now we see the fiber structure much better. And to analyze this one by one, let's also turn off the cut for now. And then we only see, as you can see here, the grain, so the horizontal lines. Now these horizontal lines, actually, as you can see here with the fracture direction, automatically find the length of the object. So for example, if we do the same with a box that is vertically aligned, let's turn off the grid, and we run a RBD material fracture over this, where the clustering and the cut is turned off for now. And you can see, as we've learned, all of this takes ages with the RBD material fracture. So here you can see cluster is turned off, cut is turned off, and all we have is the grain, and it finds the length of the object automatically. When we have something that is horizontal, like this box, with the same settings, and waiting a bit, we can see it finds the structure like this. Now be careful, if you mix two objects, for example, you have a vertical and a horizontal object, and you put both into the RBD material fracture, and again, I have cluster and cut turned off for now. Okay, after waiting a bit, we can see that it creates the wrong result, because it takes the longest bounding box and therefore for the vertical box, the structure is wrong. Now there's a trick for that, and that is up here, fracture per piece. So if you have multiple objects that you want to fracture at the same time, make sure you activate fracture per piece, because if you do, then it will find the bounding box for each object. And again, we have to wait quite a while, which is one of the big disadvantages of the node. And here you can see now, even though the orientation is a bit odd, but you can see here it's along the horizontal object, and here it's along the vertical object. So it's actually correct. Okay, so this is the first element, the grain. And we can adjust the grain in all kinds of ways. So what we can adjust here is the grain spacing. That's simply how far away they are. So if I lower the number, of course you get more grain. You can offset the whole thing, so you can push it in a certain direction, which is basically like a seed. So if you don't like the result, you can just move it around. Then on top is a seed, if you still don't like the result. And then you have the grain noise. So as you can see, the lines are not perfectly straight. They are broken up with a noise. And you can adjust that. So if I would turn this off, you can see we just get straight lines, which is not very realistic. So we can push that. And after some waiting, we can get some pretty extreme results, which is not really what we want. So let's adjust this again, maybe to 0.2, yeah, or maybe 0.15. And then you can see this gives us our, main fiber structure of our wood. Okay, so that's the first element. And now we activate the cut, and the cut does two things. First of all, it actually cuts along the line and also then creates splinters on this cutting edge. So for now, let's actually turn off the splinters by lowering the splinter density from 25 to something lower so that we can see better what's actually going on. And here you can see that the cut is actually relatively straight. I hope you can see that. So this is on top of our grain. Maybe for now we can turn off the grain so you can see that better, and that is the cut. Now this, as you can see, also has a noise. So if you would turn this off, you can see I think that might be the splinters. By the way, if you wanted, you could visualize all those things, the grain and the cut, up here with the guide geometry. So let's look at the cuts, and here you can see what it's doing. So there's still some kind of noise going on. Oh, it is the splinters actually. Okay, so let's lower the splinter length to 0. Okay, so this is actually what the cut is doing. Yeah, so this would look boring, this would look wrong. And this is why you have a curve noise on top that you can push in. And I thought that's what we saw. So this is a way of breaking up those cuts, which is great. But on top of that, it still doesn't look like wood would break, because we're missing the splinters. And this is why the splinters is so important. And now let's increase the length and the amount of splinters. And here you can see what it does with our cutting edges. So let's turn this off for now again. And here you can see what this results in. Now, if we would keep it at that and let it fall down, we would get those big bunched up pieces of our wood. Let's actually quickly do this, why not, and see how this looks like. Maybe that is what you want. And let's move our log up a little bit and so that it can fall down. Let's activate the ground plane as well. And currently, actually let's quickly lower the constraints. We will talk about constraints later, so for now let's turn them off. Constraints just, glues the whole thing together. And if I press start, you can see this is how it would look like. It's not bad, but it still feels a little bit unrealistic. And this is why usually you combine that with the grain, which is pretty much kind of what we saw in the beginning. So if we turn off the visualization of the name attribute, you can see what it's doing. Okay, so for some reason though, side effects decided that they should also on top by default turn on the clustering. So if you visualize the pieces again, this is the biggest problem I have with the defaults. It glues everything together again. So everything we broke up before is now glued together again, which is kind of weird. The smallest thing you should definitely do, if not turn it off completely, which I usually do when I go with this setup, is lowering the size of the pieces. And this is, again, the problem that I always see with the RBD material fracture. It's incredibly slow to work with this. I really don't like it. But here you can see a bit better what the clustering idea is. It depends on the size of your object. Before it looked like this, and with the clustering on, lowering the size of a cluster, it glues certain pieces together, and that can look then a bit more realistic, because not everything breaks apart completely. There you go. Some pieces stay together. And let's do this again without the visualization. And there you have it. So I think that's the best way of analyzing the RBD material fracture. Turn off the cluster in the beginning. The grain is the horizontal lines. The cut is the cut along the length. And with the splinters, you get the actual broke up zigzag lines in the cut. Those are the most important elements. And with that, you should be able to get the best out of that tool. Now, as I said in the beginning, I'm not a big fan of this because no matter what you do, first of all, it's very slow and I really don't like that. I really don't like if I change a number and I have to wait sometimes up to 15 seconds to see a result. Frankly, that drives me crazy, especially when you have more complex geometry than that log. It can take forever to run this through an RBD material fracture. But besides that, I'm not even that impressed by the results personally. This is a subjective thing, but I think for me often that doesn't look very realistic. And you might have noticed what we can't do is, at least I don't know how, we cannot rotate where the structure is. So I could not rotate it around, or I could not, cut it again so that the splinters are actually there. It's very hard to create a very splintery effect. It's always bunched up in those weird lines. So personally, I'm not a massive fan. And in the last video, in the advanced fractured video, we actually saw an alternative to that. So this can be an option, but it's by no means the only one. And for a later example, I will use the technique that we've already seen that is based on the Voronoi fracture. Okay, let's move on. That's just an option. Where I think the RBD material fracture has to offer much more is the glass shattering, because this is actually much harder to do this manually and gives pretty nice results. So this is actually something I would use. And let's start with a box, because actually we will see some problems when we just start with a simple box and we drop this into a RBD material fracture. Of course, we switch this to glass again. And here you can already see that it deforms the whole thing completely. Now, before we look at this problem, let's look at the actual pieces, and then you can see what the idea behind the glass fracturing is. And that is we have an impact point from which the cracks go away in a circular fashion. And you can see it creates a pretty weird results if you do this with a box. But the trick here is it actually expects the way glass is built by default relatively thin. And all of a sudden you can see the problems go away, because this is how the tool expects your input geometry. That's the first thing to keep in mind. And from there, it's actually relatively straightforward to understand. You have impact points, and by default, it's just one impact point, which is created randomly. So you have a seed down here where you can change that impact point, and you can also create more random impact points. This can be interesting if all you want to do is break that piece, randomly. But more often than not, what you actually want is to have a specific control about where your point is. And this is actually where the fourth input comes in. That is always dependent on the actual material type that you're using, but for points, this expects single points, which for example we could create with an add node. So let's create a point, press enter, and then you can control where it is. There it is now. And when we look at the RBD material fracture with a second input, you can see this point is ignored currently. That's because we have to first activate the input points, which is down here next to the scatter points. We could turn off the scatter points, so we don't want random points, but we want the input points from the add node. And now you can see here, let's actually make sure that we see where it really is relative to the glass, otherwise it's a bit confusing. But here you can see, if you're actually close to the glass with a point, you can see they can really control where the impact point is. And of course we can do this with multiple points as well. So here's a second one, let's move it over here to the glass. And then you can see we can create them ourselves. You can even combine that. So let's delete one point and activate the random points. Now you can see we have random points plus a point that we can control ourselves. Not sure when you need that, but just for you to know, you can combine the two techniques. So let's turn off the random points for now and just keep one single point, because then it's the easiest to explain all the elements. And mainly what we want to talk about is the cracks. And you basically have two different lines here, as you can see, the ones that go away from the center and then the small ones in between. And the ones that go away are the radial cracks, and the ones in between are the concentric cracks. So in other words, it's pretty straightforward. The radical crack number is how many lines we have going away from the impact point. More create more, less create less. Who would have thought? Then there's a variance in it. That is important when you have multiple points, so that every point has a different number. Let's quickly maybe do this. If I create scatter points again and I increase the variance and lower the overall number, you can see that this one has more than this one, and this one has so few that you can't even see that it's an impact point anymore. So yeah, this is what the number variance is for. So let's ignore this for now, since we only work with one. Then of course you have a seed to create different results. Now you would think that the breaking up of the edges here, the noise that we can see in the lines, is the next thing you can control somewhere here, but it's not. It's actually part of the detail. You can see that the lines are not straight, they are broken up, and this is what the edge noise is doing. So you can change that by changing the noise frequency. So if we increase that, we get more broken up lines. If we would lower this, maybe to 0.3, there would be more straight. Then you have the strength of the whole effect. So if I put this to 0, you can see that just straight. And then if I push it in, they are deformed. Let's actually go back to a higher frequency, see that better. There you go, straight, more broken up. And then you can make sure that it's less strong closer to our center point, because otherwise this would happen. So there is kind of a threshold. And the same is true for the edges. If you lower this, you can see closer to the edges, it would deform the whole thing. So there is kind of a safety area, and these we can control with those two numbers here. Okay, so let's say we have something that we like, and let's now talk about, back to the cracks, about the concentric crack. And this is controlled by, okay, how many do you want? You can control by the minimum distance between them. And then the spread controls basically how many of them are further away. So if I increase the spread, they are all, spread it evenly, so there are a lot of them. And if I lower this, you have fewer of them basically. So just play around with this a little bit. And this spread is then controlled with a discontinuity frequency and discontinuity size. So if I lower the discontinuity size, you can see the gaps are lower. So let's maybe create 80. And so that means you have really big gaps. If I go lower to 20, when you have gaps, it's not as big. So 40 in our case actually seems pretty good. And then the frequency is basically how often that happens. So yeah, this basically explains it. The best way of dealing with this is really just playing around with it and see what happens. Those kind of tools are best learned by just using them. Don't over theorize about this, just play around until you have something that you like. It's that simple. Okay, so this is really all about glass. We will talk about some problems that comes with glass breaking, but one thing I want to talk about is the chipping. We already talked about this in the concrete video, and basically this is a great idea because when we look at the result with an exploded view, for example, you can see it adds an additional level of detail. So these small pieces, those are the chips. So if I turn this off again, you can see it feels way less realistic if you only have kind of big pieces. But as soon as you add a lot of small pieces on top, it feels way more realistic. So this is a great idea. Unfortunately, be careful with this. It can create problems because the algorithm inside is often not super stable. As far as I remember, the glass chipping works better for some reason than with concrete. But be careful. If for some reason something breaks later on, or your simulation behaves weirdly or something, then try to turn this off and see if it works better. We will see alternatives to that by emitting additional geometry after the simulation that then feels like it's chips. So this one is a good idea, but really dangerous in my experience. This is why it's turned off by default, and I would encourage you to use this in a very careful way. So one last thing, as we've seen, the glass fracturing expects a flat surface. But what if a flat surface means a sphere that we poly-extrude slightly? So there is a certain thickness. Let's quickly use a clip to show this. So here we go. When we look from the side, there is a thickness to it. And while this might be an extreme example, you don't often have a glass sphere, but let's say, the front window of a car is curved, and there are many of other examples like that. And the problem is, if we would now bring this into the RBD material fracture and set this to glass, you can see multiple problems, basically the problems we had in the beginning. First of all, for some reason, it deforms the whole thing, and also it creates some really weird shapes. So this doesn't really look as believable as the ones that we saw before. And this is based on the underlying algorithm. The default algorithm expects not only a thin object, it also expects a relatively flat object. And up here, you might have noticed this, you can actually change that from flat panes to curved glass. And if we turn this on, It takes a while, of course, and then you can see there's a much nicer result without any broken distortions. And if we quickly create 2 impact points, you can see it even better. And let's change the C to find something that is further away from each other. There you go. So this even works with multiple impact points on different sides. And if we adjust this a little bit, we can actually get some pretty nice results. Let's maybe do this with an exploded view. There you go. Even for round surfaces. This is new in Houdini 20 because side effects noticed that this is potentially a problem. So curved glass, if you really have something that is round, is something we have to activate, which you can with Houdini 20 to get the right results. All right, so that much as an overview over the glass and the wood fracturing in the RBD material fracture. Again, we will talk about both materials in later videos, but for now I hope this is helpful. So thanks very much and see you later. Cheers.